We are continuing with applications of renewal processes in various other contexts. So in this module, we are going to start with an inventory example. So in the inventory example, what we'll follow the very standardized or standard so-called SS policy of inventory, wherein little s, there are two quantities, little s and capital S, which are fixed in the policy. Little s is the size such that anytime the stocks or inventory size goes below s, then immediately a fresh order is placed to bring the inventory back to level capital S. So that's the side of the inventory policy, whereas then there are customers coming in successively and their demands are assumed to be random IID, and a cycle means that a cycle starts with an inventory being put at capital S, and then as newer and newer customers come in, they place demands, and the moment as a result of demand of a customer, the inventory falls below little s, immediately an order is placed to bring back the inventory to the level capital S, and a new cycle starts. So that's how the cycles are done. And what we have proved in this is that we are not proved, we are going to look at essentially the time that is required for the inventory size to go below x at any point of time. We would find the limiting distributions, etc., of that using the alternating renewal process result. Then we introduce another concept called renewal reward processes and see some applications of that. So now we want to look at an inventory example. Customers arrive according to a renewal process with a non-lattice inter-arrival time, which is f, distributed as f. That means successive customers arrive, the time between successive arrivals, their IID, and have distribution f. Order volumes of successive customers are also random and their IID with distribution g. And the store follows. This is a very standard ordering policy or inventory policy, which is denoted little s, capital S policy. I'll call it SS ordering policy. What is it? If the inventory after serving a customer goes below little s, order is placed to get the inventory up to capital S immediately, otherwise no order placed. So basically, every time by serving a customer, the inventory goes below little s, immediately the stocks are updated to capital S by placing a new order, which is immediately served. And no orders are placed until that happens. Okay, so let xt be the inventory level at time t. So what we want to find is the limiting distribution of xt, more specifically for any x positive, what's the limit that pxt is greater than or equal to x? So in the long run, what's the probability that the inventory level would be more than or equal to x? So assume that x0 is s, that is when it starts with a full inventory, maximum inventory level, which is capital S. Say that the system is on when the inventory level is greater than or equal to x, otherwise off. Okay? And what is a renewal cycle? A renewal cycle is a time since the inventory level is put in capital S until the inventory falls below little s, because that's a time when again an order is placed and the inventory level is brought back to capital S, which means the whole thing starts all afresh. So that's a natural renewal cycle. So we have an alternating renewal process with this on and off defined as we have. So during a renewal cycle, on period is that period when inventory level is greater than or equal to x, otherwise it's off. So by using the results from alternating renewal process, what we have is limit t going to infinity, probability that xt is greater than or equal to x would be expected on time in a cycle divided by expected length of a cycle. How do we find out the expected on time in a cycle and expected length of a cycle? So for that, let y1, y2, etc. denote the successive customer demands, which are assumed to be IID with a common distribution G. And let t sub y for any y be the minimum of all those n's such that y1 plus y2 plus yn is greater than s minus y. Okay? So yn is sort of the first time that the total demand up to that point of time placed by successive customers exceed s minus y. Okay. So it is the tsth customer that ends a cycle. So if you put y equal to s, look at ts. ts is the first time that after serving a customer's demand, starting from an inventory level of capital S, after serving a customer's demand, ts is the first time the inventory level goes below little s, which means that the cycle ends. So cycle ends with the tsth customer, of course, and the txth customer that ends the on period in a cycle, because on period is that period during which the inventory is greater than or equal to x. So it's a txth customer that ends an on period in a cycle. So tsth customer ends the cycle and txth customer ends an on period in a cycle. So we have assumed that the customer demands are independent of arrival times of customers. Therefore, the limit of probability xt greater than or equal to x, limit of that as t goes to infinity, equals expectation of summation yi, I ranges from 1 to tx, because the txth customer brings an end to the on period, divided by expectation of summation yi, I going from 1 to ts, because the tsth customer ends a cycle, which of course equals etx by ets. So what is it that is being used here? What we are using here is that the arrival times of the successive customers are independent of the y's, the demands. Okay. So now consider a renewal process to be called n sub gt, whose interarrival distribution is g. Remember, g is the common distribution of the successive demands of customers. So y1, y2, yn, etc. are IID with distribution g. It then follows immediately that ty minus 1 is ng at s minus y. That is the number of customers for which the demand goes below y, level y, the first customer for which the first time that it goes below y is precisely this one. Now, denoting the renewal function associated with the process ngt by mgt equal to expectation of ngt, which of course is, as we already know, is sum n equal to 1 to infinity g star nt. So here the distribution of the interarrivals for this renewal process is g. So this is the n-fold convolution of g. So one finally obtains that limit as t goes to infinity of probability that xt is greater than or equal to x is 1 plus expectation of of ng of x minus x, that would give you the expectation of Tx, divided by the expectation of 1 plus mg of s minus little s, which gives the expectation of Ts. So the most important here is this understanding that with this new renewal process ng, for any y, Ty equals or Ty minus 1 is ng of s minus y, where ng is this renewal process whose interrival distributions are g. So successive demands are y1, y2, yg, and they are the interrivals. So that's we get this result. We now want to define a new concept which would have again lots of applications. So far we have been mostly using the idea of modeling other examples through alternating renewal process and defining on and off cycle depending on what is of interest to us. We introduce another important renewal process which is called the reward renewal process, which also would be very useful in many applications. We'll see that later. But let's first say what is a renewal reward process. So we have an usual renewal process with interarrival times x1, x2, etc., which are IIDF. Now where do the rewards come in? Assume that each time a renewal occurs, we receive a reward. So let's R1, R2, etc. denote the rewards received at successive renewals. They are random. So assume that the successive reward amounts are IID, but we allow Rn to depend on Xn. So that we allow. So essentially what we are saying is that if you look at the pair R1, X1, R2, X2, R3, X3, etc., they are IID, and that of course would mean that the marginals R1, R2, etc. would be IID. The marginals X1, X2, etc. are already IID, but we allow dependence between Rn and Xn. So essentially that's what I said. Xn, Rn, these pairs are IID random vectors or random pairs. So let's now denote RT to be the total reward earned by time t, which of course is exactly equal to sum from n equal to 1 to nt, that is the random number of renewals taking place up to time t, and then we add the corresponding rewards R1, R2, etc. up to Rnt. That gives us the total reward earned by time t. Now here is the main result. So as t goes to infinity, first of all Rt by t, which is a random variable, Rt is a random variable, that converges to E of R divided by E of X with probability 1. And secondly, we have this same convergence also in expectation, which is that E of Rt divided by t also goes to the same ratio, which is Er over Ex. Of course, these are all assuming that Ex is finite. So, important remark, we are just going to apply this result. Important remark is that even though we might have given the impression that get the reward at the end of a cycle, but frankly speaking, it's not necessary. So, although we talked about successive renewals received at each renewal, it is not actually necessary that the rewards have to be actually received only at the end of the renewal cycles. One may allow the rewards to be received gradually during a cycle. If we now define Rt as a total reward received until time t, then the theorem still remains valid. Okay, so there could be rewards coming from the cycles, etc., that ended at time Snt, but then there could be rewards until time t also after that. So let's go to an example of alternating renewal process. So assume that reward is 1 per unit time when the system is on. So during any cycle, during the period when the system is on, your reward is 1 per unit time. No reward for the off time. So then it's clear by the definition that Rt would represent the total amount of on time during 0 to t. Since the total reward during a cycle is same as on time during a cycle, which is Z1, so we get that the amount of on time during 0 to t over t converges to expectation of total reward during the cycle, which is expectation of R1, which is expectation of Z, divided by the total expectation of total renewal cycle, which is Ez plus Ey. So you see, Applying this result, we are now able to show that the amount of on time during 0 to t divided by t, that proportion converges to Ez over Ez plus Ey. Now this is not so intuitively, not so unexpected or surprising. So as t grows, the proportion of time, out of the whole time, the proportion of time that the system was in on stage, in the long run it becomes expected on time divided by expected length of the cycle. Now let's look at average age and excess. We'll again get this by applying reward renewal process result. So consider the age process AT in renewal process with a non-lattice interarrival f. What we now want to find is a very interesting quantity. So look at sort of age averaged over time. So precisely integral 0 to t as ds divided by t, and we want to know the limit of this. So assume, to go about it, assume that one is paid money at a rate equal to age of the process at that point of time. That is, at time s, one is paid at the rate as, which is the age at time s. Thus, the reward received during 0 to t, which is rt, would be nothing but integral 0 to t as ds. So let's say that the amount of reward is actually at time, received at time is actually as. Therefore we get this. Next, denoting x to be the length of a typical renewal cycle, note that during a typical cycle, if I look at integral 0 to x sds for capital X random, this would be x square by 2. So this is a reward during a cycle would be x square by 2. That is because as time passed by in a cycle, the age is s during the whole interval 0 to x. So as s varies over 0 to x, you keep on getting reward s at time s. So the total reward during a renewal typical cycle would be x square by 2. Now using the result on renewal reward processes, what we therefore get is that this quantity 1 over t 0 to t as ds, which is same as rt over t, converges to the reward, expected value of a reward during a typical cycle, which is half of ex square, divided by the expected length of a renewal cycle, which is ex. So we get e of x square by 2ex as a limit of 1 over t 0 to t as ds. So let's continue with that. Similarly, if you recall the serial drive process yt, once again we can do similar things with yt. Look at the limit 1 over t 0 to t y as ds, and by the same argument exactly as before, now reward is given at time s at the rate ys. So you can argue exactly as before to get that 1 over t 0 to t y as ds converges with probability 1 to the same ratio, which is e of x square by 2ax. Now if we consider the sum of these two things, at plus yt, which is xnt plus 1, which is, remember, is simply the length of the renewal cycle at t, then from what we have done before, we deduce that 1 over t integral 0 to t xnt plus 1 dt, which would be the same as 1 over t integral 0 to t as ds plus 1 over t integral 0 to t y as ds. But since both of these terms, each of these terms converts to the same limit, this 1 over t integral 0 to t xn plus t xnt plus 1 ds or xn s plus 1 ds would converge to the sum of those two limits, but since the two limits are same, it will be twice that limit, which is e of x square over ex. So let's end with a remark, which is that e of x square over ex, we all know, is always strictly larger than ex, unless of course x is a constant random variable, because this is strictly larger than ex means that the variance is strictly positive, and we know the variance is strictly positive unless x is a constant random variable. So what is it says that if you look at the average value of x and t plus 1, in the long run. So by average value of x n t plus 1, what we mean is for any t, you integrate 0 to t x n plus 1 ds, divide that by t, then that ratio goes to with probability 1 to e of x square by ex, which is greater than ex. So roughly what it says, the average value of x n t plus 1 in the long run is greater than ex. Okay, so this is again roughly had something to do with length of a renewal interval at time t seems to be generally larger than a typical renewal interval. Short, in this module what we saw was, as promised, we started with an inventory example, so application of the renewal theory, or more specifically alternative renewal process theory, in the context of inventory analysis or this inventory application. But then after that we introduced a very important, another important notion, as important as the alternative renewal processes, namely renewal reward processes. So here basically for every cycle you receive a reward. The reward doesn't have to come at the end of the cycle, it can be earned continuously and so on and so forth. But then we had a result which we stated for reward renewal processes, and for reward renewal process, we have this theorem, and then using that theorem we can then apply it to various other contexts to get results on that. In particular, for example, we had this analysis that was already done on residual life, excess life, etc., etc. Earlier we had found limiting distributions of excess life or residual life and age at time t. We found the limiting distributions of those things, but now what we will look at is we looked at the time average of the age at time t and residual life at time t, and we were able to find with probability 1 or almost shear limits of this using reward renewal processes.